Okay, good day. This is dual enrollment pre-calculus. I am Mr. McCulley, and this is lesson number 21, graphing tangent, secant, cosecant, and cotangent functions. Let's get to it. So those are the learning goals as well. The last one says we're going to talk about damped trigonometric functions, and that's just going to be trigonometric functions that follow a different equation, and they're kind of neat looking. And so we'll get to those as we get to it. The good news is that we're adding the other trig functions, and that tangent, cotangent, secant, and secant all have vertical asymptotes because they're divisions by zero. All four of those trigonometric functions are defined as a quotient of other expressions, and so there's the possibility that we have a divisions by zero. And then we also have to keep in mind that tangent and cotangent do not have an amplitude. Secant and cosecant technically don't have an amplitude either, but we are going to use that same process to find maximums and minimums again. So the good news is we're not changing our method. The method that we learned in the last lesson is going to be exactly the same as the method that we're using in this lesson. We just have some different functions that have a little bit different shapes. The sine and cosine function had nice, smooth, undulating waves. These don't, and they have the addition of your vertical asymptotes, but the process is still going to end up being the same. And so we're going to find the amplitude, we're going to find the period, make the quarter turn divisions. We're going to check to see if the bx minus c has a c equal to 0. If so, we start at the origin. If the bx minus c has something other than 0, we're going to have to find new endpoints for the first period. We're going to plug in some points, and we're going to draw our curve. So let's start with a real simple one. Let's start with tangent of x. And so if I start with the tangent of x, I'm going to recall that the tangent of x, there's a quotient identity that says tangent is equal to sine of x over the cosine of x. All right, so since there's no other expressions in there, and tangent and cotangent don't have an amplitude, we'll start with a period. And we know that it would be just 2 pi. And full disclosure here, tangent actually has a period of just pi units, but just so that we can keep everything nice and consistent, we're going to continue using that 2 pi. Just understand that the period of tangent is just pi units. And so if I call this 2 pi, this one becomes 4 pi. And so if I break them up into those quarter turns again, I've got pi, I've got pi over 2 here, and then I've got, let's see, we're counting, starting with 0. So 1 pi over 2, 2 pi over 2, 3 pi over 2 doesn't reduce, 4 pi over 2 is 2 pi, 5 pi over 2 does not reduce, 6 pi over 2 is 3 pi, 7 pi over 2 does not reduce, and then 8 pi over 2 becomes 4 pi. All right, so again, we have no period. We don't have any up-down shift. We're pretty good. We can start plugging in, and we'll start with 0. So if I start with 0, the sine of 0 is 0. The cosine of 0 is 1. So 0 divided by 1 is 0. There is our first point. We're started. All right, as I go to pi over 2, let's plug in pi over 2. Well, pi over 2, the cosine of pi over 2 is 1, this point right here. Pi over 2, the cosine is 1. The sine, though, is 0. So I've got a division by 0. So already I've got a vertical asymptote here. So since there's a vertical asymptote, I basically have two choices. It can either start here and go up, or start there and go down as we get closer to pi over 2. And the way that we figure out what it does is we ask ourselves what happens as we go from 0 to pi over 2. Well, in this first quadrant here, both the x values and the y values are both positive. So the sine is positive, the cosine is positive, so positive divided by a positive would be positive. So this function has to go up like that because all the values are positive. Now, as we go from pi over 2 to pi, all right, let's see. Pi, the sine of pi is 0. The cosine of pi is -1. So I've got 0 divided by -1. That's 0. But again, I have two choices. It can either come up from the top and go to 0, or it can start at the bottom and come up to 0. Well, we have to make that determination. In this particular quadrant, as we go from pi over 2 to pi, we know that the x values are negative and the y values are positive. So I get a positive divided by a negative because sines y and cosines x. And so positive divided by a negative is negative, so all of these values must be negative, and it goes to there. Now as I go to 3 pi over 2, all right, 3 pi over 2, the sine of 3 pi over 2 is negative 1. The cosine of 3 pi over 2 is 0. So again, I get another vertical asymptote here at 3 pi over 2. So to decide which way it goes, I have to determine what values are in here. Well, x is negative, y is negative. Negative divided by negative is positive, so every value on this interval must also be positive. And to finish it off, as I go from 0 to 2 pi, at 2 pi, we get a sine is 0, and the cosine of 2 pi is also back to 1. So I've got 0 divided by 1 is 0. And so to determine how I draw that shape in, I have to determine what happens as I go from 3 pi over 2 to 2 pi. In this particular instance, the x's are positive and the y's are negative. So I get negative divided by a positive, that's negative. So all of the values on this interval have to be negative, and I just connect the dots. So now, if I copy it, because we've gone all the way around, copy what I've already shown, it becomes fairly simple to finish off the graph, and we see a nice clean periodic function for tangent. All right, let's move on to something that's a little bit more challenging. Let's talk about the graph of the trig function y equals 2 secant 4x plus 2. So I see a couple things here. I'm going to put the amplitude in parentheses because, again, it's not really the amplitude, but it just gives us an idea, and it links us back to what we did in the last one. And that's going to be the absolute value of 2, which is going to be 2. And then our period is still going to be the 2 pi divided by the b value. In this case, it's 4, so we get pi over 2 as our period. And then we have a translate 2 units up. So our center line is going to go from the x-axis to the line y equals 2. So let's put that in there too. And then we have that amplitude 2. So just like in the last one, we go 2 up to get to 4, and then 2 down and we'll be at 0. Okay. So now let's make our period. And so here it's 2, you know what, let's put it up above here. You'll see why in a second. So I get pi over 2 is my first one, and then if I go over another pi over 2 units, I'll be at pi. If I divide that in half, I'll have pi over 4. If I divide those two in half, I'll have pi over 8. So we're counting by pi over 8. So I got 1 pi over 8, 2 pi over 8 is pi over 4, 3 pi over 8 doesn't reduce. 4 pi over 8 becomes pi over 2. 5 pi over 8 doesn't reduce. 6 pi over 8 becomes 3 pi over 4. 7 pi over 8 doesn't reduce. And 8 pi over 8 is just 8. All right, so let's start plugging in some values. Now, before I do that, what I want to do is I'm going to change this to y equals 2 times 1 over the cosine of 4x, because I memorized my unit circle in terms of cosine. That will make that a little bit easier. And we're just using a reciprocal function, so it's not that big of a deal. All right, so let's plug in. Plugging in 0. 0 times 4 is 0. The cosine of 0 is 1. 1 divided by 1 is 1. Times 2 is 2. Plus 2 is 4. So 0, 4 is our first point. Pi over 8. Pi over 8 times 4 would be 4 pi over 8, which is pi over 2. That's good. The cosine of pi over 2 is 0. 1 divided by 0 is undefined, so already, again, we have a vertical asymptote here. So we have a couple of options, and our value can either start here and go up or start here and go down. Now we have a couple of arguments. We know that it can't go down because there's no value for x that we could plug in here that would make the function equal to 0. There's no x-intercepts, so it has to go up. The other thing is that from 0 to pi over 2, the cosine values are positive, so I get all positive values here. So it's going to go up like that. All right, so we hit pi over 4. The pi over 4 times 4 is just pi. The cosine of pi is negative 1, so I get 1 divided by negative 1 is negative, negative 1 times times 2 is negative 2, plus 2 is 0, so at pi over 4 I've got 0. Now it can either come down from the top or come up from the bottom, and we have the center line. So all of these values are going to be negative and they're going to get very big. So we're going to go like this. And then if I plug in 3 pi over 8, 3 pi over 8 times 4 would be 3 pi over 2. And the cosine of 3 pi over 2 is 0. So I got another division by 0, which is going to give me another vertical asymptote. And then again, in the third quadrant, as we go from pi to 3 pi over 2, cosine's still negative, so it's going to stay negative there. And then pi over 2 times 4 is 2 pi. The cosine of 2 pi is 1. And so 1 times 2 is 2, plus 2 is 4, so at a half, I'm back to 2. And we can probably guess that in the fourth quadrant, since cosine is positive, we're going to have a value that looks like this. We've completed one period. If we just go through and we copy the remainder of it from the period before, we get a nice periodic graph that looks like this. Pi. All right. Let's talk about a cosecant one. And again, we're going to do a cosecant one where we have to change our period just a little bit. So our quote-unquote amplitude is going to be equal to the absolute value of a half, which is just a half. Our period is 2 pi divided by the 2 there, so it's just going to be pi. There is no, got ahead of myself, no up, down translation. All right, and because we have a c value that's other than 0, we're going to find new endpoints. So let's see here, I get 2x minus pi equaling to 0 and 2x minus pi equaling to 2 pi, the endpoints of the standard trig function. And so let's see here, I add pi to both sides, I get 2x equals pi, x equals pi over 2. I add pi, so 2x equals 3 pi, and so x equals 3 pi over 2. And if I take a difference between 3 pi over 2 minus pi over 2, I get 2 pi over 2, which is just a period of pi. So we're fairly good with that. So I'm going to go here is 2 cosecant. Yeah, we'll do that. Pi over 2 is my first period, and then 3 pi over 2 ends that period. And so let's see, if I want to add pi, so there are 2 halves in one. So in pi, there are 2 pi over 2. So if I add 2 pi over 2 to 3 pi over 2, I'll get 5 pi over 2. And so if I divide that into half, I got 1 pi over 2. This will be just pi because it would be 2 pi over 2. Halfway between that would be something pi over 4. And so if I'm counting by pi over 4 now, this would be 2 pi over 4. So this would be 3 pi over 4. This would be 4 pi over 4, which is pi. 5 pi over 4 doesn't reduce. 6 pi over 4 is 3 pi over 2. That's good. Let's put those in there. So I would have 7 pi over 4. 8 pi over 4 is 2 pi. 9 pi over 4 doesn't reduce, and 10 pi over 4 is 5 pi over 2. That's good. Now, since our amplitude is a half, we're going to go a half there. We're going to go negative 1/2 there. We're going to start with our values. So pi over 2 times 2 is pi, minus pi is 0. And remember that cosecant, so let's rewrite this just over here. So we'll say it's y equals 1/2 times 1 over the sine, because that's what cosecant is, 2x minus pi, and no up-down shifts, so we don't have to worry about any of that. So I get 0. The sine of 0 is 0, so I have an undefined. So right off the bat, our first value is going to be a vertical asymptote. 3 pi over 4 times 2 will be 3 pi over 2 minus pi is just pi over 2. The sine of pi over 2 is 1. So I get 1 divided by 1 is 1 times a half is a half. So I have a half here. Remembering that sine is always positive in the first quadrant, we know that we get there. Pi times 2 is 2 pi. 2 pi minus pi is just pi. The sine of pi is 0. So again, I have another vertical asymptote in the second quadrant. Sine is positive, so all those values are going to be positive. And then let's see here, 5 pi over 4 times 2 is 5 pi over 2. And 5 pi over 2 minus pi is 3 pi over 2. The sine of 3 pi over 2 is negative 1. 1 divided by negative 1 is negative 1 times a half gives me negative a half. And in the third quadrant, sine is negative. And then you can probably see where I'm going with this. And we've done almost a full period here. If we just follow what we did in the first one, I get something that looks like this. All right, so damped trig graphs, we're not going to do a whole lot of graphing with these, but basically the way I look at it is two different values. So here is the basically I'm just going to say that it's the graph of a line or a curve. So this is the equation. We're going to graph y equal to x, okay? And it's negative because sine can be positive or negative, y equal to negative x. So we're just going to make this part positive and negative. And then we're going to use the sine values to get the rest. Now we're not going to do a bunch of these by hand, so I just want to kind of quickly give you an idea. And so the graph of this thing is going to real quick look like this. So I've got my line y equals x right here. I've got my line y equals negative x right here. And then the sine, remember, sine changes from 1 to 0. So when sine is 1, we're going to have the full y equals x value. And when sine is 0, 0 times whatever that is going to give me 0. So I'm going to have a curve that's going to kind of look like this. Kind of go like this, and then touch, and it's going to go up and down. And when I get these damped curves, it's going to get wider, whereas the other ones were consistent. So basically, we're going to graph most of these by using the graphing calculator. So x sine x. Let's make sure our mode is in radian mode because that's what we want. Hit. I didn't want to do that. Mode. Go down here to radians. Hit enter. Hit graph. Oops, we didn't see that. So zoom 6 on standard zoom. And so you see that. Now if I went in there and went y equals x and y equals negative x, you're gonna see that it does touch those points. And this would be where the sine is equal to 1, and this is where sine is equal to negative 1. That's where sine is equal to positive 1. And these points right there are where sine is equal to 0. All right, that's really all I want to say about that. Let's do one application problem and move on. And so this is an application problem. It talks about a pulley system that changes I didn't write the whole sentence out simply because it takes a while, but I'm going to read it to you. It says here, a cross belt connects a 10 centimeter pulley on an electric motor with a 20 centimeter pulley on a saw arbor, and it says show the figure. The motor runs at 1700 revolutions per minute. So This right here is, so we've got a little electric motor here that's got a little band pulley, and then this one turns a saw blade. And so this one right here is 10 centimeters, and this one is 20 centimeters. All right. And they want us to consider this to be an angle theta right there. And so just kind of going back some things that we want to know from geometry. When you have a tangent line, and this is going to be a tangent line, it's going to be perpendicular to the radius of where it touches. So we've got a bunch of right triangles here, and we're trying to keep this as clean as possible. It's going to get messy, but we have the small one is turning at, let's see here, 1700 revolutions per minute. All right, so it wants us to determine the revolutions of the saw. So for every one that this turns, we want to figure out how far that turns. All right, so if the radius is 7 centimeters or 10 centimeters, so the circumference would be 2 pi times r. So in the small one, c equals 10 of the 10 centimeter one, it would be 2 times pi times 10, and then in the other one, and again, which would be 20 pi, c, the bigger one, would be 2 times pi times 20, which would be 40 pi. So basically, this one is twice as big as this one. So for every time that this one's going to go around, this one's only going to go around a half of that. So essentially, if the small wheel is turning at 1700 revolutions per minute, the bigger saw is only going to move at half of that rate, which in this particular case, half of 1700 is going to be 850 revolutions per minute. All right, so how does crossing the belt affect the saw in relationship to the motor? So if the saw is going this way, it's going to be pulling this wheel this way, and so it's going to pull the other wheel in the opposite direction. So pull the saw in the opposite direction. All right, let L be the total length of the belt. Write L as a function of theta measured in radians. So what they're saying is theta will change dependent upon how long this line that goes from the center to the center. So if they're further away, the belt will be longer, but the angle will be smaller. So we want to find the full length of this thing. So I'm going to call it L. So L. And so if you think about it this way, I have from here to here, I'm going to call this L1 capital. And so this distance here will be L1, and that distance will be L1. From here to here, we'll call that L2, and then that one will be L2. All right, and so then, and again, it changes from here around to there. I'm going to call that P1, and for this one, I'm going to call it P2. So L is going to be the sum of two L1s plus two L2s plus P1 plus P2. So it's going to be all of these lengths added up. And so we want to figure out what that value is going to be. All right. So let's start calculating some of this stuff. All right. If this is theta, then this side right here is an opposite side, and this side here is an adjacent side. Same from here. So because what do I call it? Vertical angles are also congruent. So I've got a theta also right there. All right. So this L1, the tangent of theta will equal the opposite side, which is a 10 over L1, and then L2, the tangent of the same theta, will be 20 over L2. All right, so if I solve for L1, I can say that L1 is equal to 10 over the tangent of theta, and L2 would be equal to 20 over the tangent of theta. And the good news is both of those thetas are the same, so I can come down here and start filling in the blanks. I got L 2 times 10 over tangent, and then plus 2 times 20 over the tangent of theta. All right, so let's figure out what P is. Well, P, if you remember that the arc length equation is S equals R theta, but we're going to call it alpha because we've already used a theta. So our arc length is S equals R theta. All right, so our R alpha. And so if this is theta here, then this one here, and this one's 90, then this one will be 90 minus theta, and this one will be 90 minus theta, and then this angle here will be this alpha, this lowercase alpha. So before I can do that, talking in terms of radians, did I do it? I didn't do it in terms of radians. Let's change that to terms of radians. Ooh, I didn't want to do that either, but hey, we had a big eraser. What are you going to do? So 20, let's call it a pi over 2 minus theta, and pi over 2 minus theta. That we keep it in terms of radians, and because it says right there it's measured in radians. I made this simple mistake there. All right, so all the way around a circle is 2 pi. All right, and so that'll be equal to the alpha that we're looking for plus pi over 2 minus 90, or excuse me, minus theta, plus pi over 2 minus theta. And that's what this thing is going to be equal to. We get all the parts, are all this first part, pi over 2 minus theta, pi over 2 minus theta plus alpha equals an entire circle, so we get that much. So let's simplify that and solve for alpha if we can. I think we can do that. So I get 2 pi equals, let's see here, alpha, and then pi over 2 plus pi over 2 is just pi. Negative theta minus theta will be negative 2 theta. All right. And so if I bring this over, I get pi plus 2 theta is equal to alpha. So I subtract pi, that gives me 1 pi. I add pi over 2, or 2 theta to both sides. It gives me plus 2 theta. So alpha equals 2 theta. So since alpha is equal to pi plus 2 theta, and even though it's a different circle, okay, this one here is still pi over 2 minus theta, and this one is still pi over 2 minus theta. And so that's still another alpha. All right, so we'll have 2 of these SR thetas, but one is going to have a radius of 10, and the other one's going to have a radius of 20. So we're going to do that. So we have, let's do it this way. P1 will equal 10 times the quantity pi plus 2 theta, and then P2 will equal 20 times 1 or pi plus 2 theta. All right, so let's plug that in. So 10 times pi plus 2 theta plus 20 times pi plus 2 theta. That's our L. Now, if you wanted to, you could leave it like that. That's not a big deal. But let's simplify just a little bit at least, and say L is equal to, well, let's factor out a 2 from both of these two, because I got a 2 here and I got a 2 here. So 2 times 10 over tangent theta plus 20 over tangent theta. And while we're doing that, let's factor out pi plus 2 theta out of these two terms. That'll leave me 10 plus 20. And so since I have a common denominator here of tangent, I'm going to say that this is 2 over, or 2 times 30 over tangent theta, and then plus, let's see here, pi plus 2 theta times 30. And let's see, do I want to make any other changes there? I suppose I could simplify and factor out a 30 and move the 20 over there. So I could say it's 30 times 2 over the tangent theta plus pi plus 2 theta. That's good enough. We'll leave it as that. There's my value. It wants us to complete a table. Well, all we need to do is plug that into a graphing calculator and fill in the blanks. So I'm sure you guys can do that. We've already done the hard part. And this lesson is starting to get long. I'm sure you're ready to be done. So let's call it a day. And if you need me to fill in the blanks, we'll do it in class. But the Star Wars fun fact of the day, Donnie Yen, a famous Chinese martial artist, plays Chirrut Imwe, a guardian of the Wills in Star Wars Rogue One. Donnie suggested to the director that they make his character blind, as it would add another layer to the depth of the story. He wasn't originally blind in the original script. So that's all I got for today, folks. That's a long one. I apologize, but you gotta do those sometimes. Have a good day. See you in class. Goodbye.